Thank you very much. I also want to thank Chris Bell for the introduction and the invitation for me to speak here tonight. So good evening. I looked on your website and on your mission statement, and it included the phrase to promote knowledge in navigation and its associated sciences, including positioning, timing, tracking, and conduct of a journey, whether in, on, over, or under land, sea, air, or space. And I thought that was particularly relevant for what I'm going to be talking about tonight, because certainly in capturing and processing aerial photography, positioning and timing and tracking are absolutely paramount in creating accurate data for use in all the applications you are going to see. So I'm going to talk you briefly through how we capture and how we produce mass capture aerial photography datasets. So as Claire mentioned, our main contract at the moment is to maintain an imagery load of the whole of the UK for the UK government. So this is, you're looking at captures of 50 to 80,000 square kilometres of data a year. So it's large scale capture, update programs, and the logistics that are involved in that. So I'll start with a little introduction of what is aerial mapping. So it's a collection of information from an airborne platform, most notably, but not exclusively aerial photography. It's a snapshot of the Earth at a particular instant in time. And it contains mass data and can be interpreted for a range of purposes. So it can be collected from a range of platforms: aircraft, helicopters, UAVs, drones, obviously also satellites. I'm going to be talking about the capture from aircraft, which is what we use for the projects we work on. So I've got a few slides to give you a bit of historical background. So the oldest surviving aerial photograph was from 1860, captured from a balloon at 1,200 feet. And the first aerial photograph captured over Paris was in 1858, which is 45 years before the Wright brothers pioneered powered flight. But photography really took off, as with many sources of technological advance in the military, and it's extensively used in the First World War. And many of the techniques used to capture an image and process the images today were pioneered in the First World War. And there's an example of an image of German lines at 8,000 feet. And then, commercial surveying began after the First World War with a British company called Aerofilms. And as is the case today, vertical imagery captured was typically used to aid in the creation of mapping. So one of the main applications, as you'll see, for updating aerial photography is the updating of topographical mapping. And it was used even more extensively during World War II for reconnaissance. And there's one slide I haven't put on there, which people always remind me about. There was a huge program of aerial photography in the 1940s after the war, which was the first mass survey of the UK. It showed all the bomb sites and the destruction after the World War II Blitz. So moving on, so Getmapping, a little bit of the history on Getmapping. So Getmapping was founded in 1998. The reason was to capture the first national aerial photography dataset, which was called the Millennium Map, and was captured with analog cameras. So this was a speculative capture. And we captured the data and went out and sold it. And this is all pre-Google days. Then moving forward, we've always been early adopters of new technology. And as you'll see in this talk, it's always key to keep up with technology. So we were the first company to adopt digital camera technology in 2004. We merged with Geosense to expand in 2011. And last year we had 40 staff across 2 sites in the UK and in Cape Town, South Africa. So we're a leading supplier of aerial photography to the UK market, and we're also pioneers of online delivery, web feeds of geographical data. So we've been feeding data to local authorities, businesses using a web shop and through web feeds for the last 15 years. And we've also long-term OS partners as well. As I said, the main contracts, our bread and butter, have been mass capture. So maintaining countrywide data layers. So we've got contracts for the Scottish Government, and then we've been maintaining a layer for Defra for the UK government since 2014. We've also supplied data to the Ordnance Survey. And as Claire mentioned in her introduction, we've also done projects in Northern Europe as well. And we've also done large-scale imagery supply for the likes of Google, Bing, Apple, and large utility companies. So all of this points to mass capture and maintenance of large data sets. And this talk will explain how we fly it and produce the data. So the first section is on data capture. As I mentioned, we've always been early adopters of technology, and technology changes quickly, and you need to keep up with it. So the first slide really shows the trend in survey cameras, and the evolution really is it's going towards larger cameras, larger image footprints, higher flying heights, and it's less flying time, and that's critical. As you'll see, especially in the UK, it's a very difficult environment in which to capture data for two reasons. One is the weather. You get very few opportunities. It's a very cloudy country. And also it's a very, very busy airspace. So air traffic is a huge factor in restricting where we can go. So you need to make the most of your opportunities, especially when you've got your 80,000 square kilometers of data to capture in a year. So the use of technology to maximize what you capture and reduce your flying time is critical. So the change in technology, the trend has really helped. So as you can see, we mentioned flying footprints. So the footprint is the area of an individual photograph on the ground, and increased and improved CCD sensors mean there's more megapixels in each sensor. Therefore, the photographic footprint is larger. So you need less photographs, less flight lines to cover the same amount on the ground. So less flying time means you can actually up your update cycle. So we're now working on contracts where we're updating the UK 240,000 square kilometers every 3 years. So you're pushing 80,000 square kilometers of data into the layer every year. And you need the technology to enable you to achieve this. So what is that technology? So we use large format digital cameras. These are the best of breed, called ultra cams. They are the market leaders. So we have got two systems with two different lenses, and this is quite important. So we've got a one lens, a 210mm focal length lens that enables us to capture at 19,000 feet for 12.5 centimeter resolution data. So what is 12.5 centimeter resolution? That is 12.5 centimeter is 1 pixel on the ground. So 1 pixel in our imagery represents 12.5 centimeter, which is our typical capture resolution for updating the UK. We've also got a 100mm lens that captures the same resolution, 9,000 feet. So you've got two different heights, which is really important when it comes to air traffic, as you'll see a bit later on. The cameras have 4 color bands. So you've got the red, green, and blue. And we've also got a near infrared lens. The way they work is that they've got panchromatic lenses, which provide the detail, and they are merged with the color bands, and you can produce high quality red, green, and blue imagery, or color infrared, or 4-band red, green, blue, and infrared imagery. So you've got quite a variety of outputs you can derive from the same photograph. Now we've got a camera. The camera sits in an aircraft, and obviously the aircraft is a very turbulent environment. So we need something to dampen out the vibrations of that aircraft. And the yellow thing is a gyroscopic mount. The mount sits over holding the fuselage, and it compensates for the motion of the aircraft, which is critical. And again, one of the main themes, and we come back to our navigational credo, is that positioning and the accuracy of positioning is critical. So what we're doing is we're taking a series of photographs of a lumpy 3D object, the Earth, and we're ultimately wanting to merge them together into a 2D map projection. So therefore, the relative position of every photograph to every other one is critical. So we need to get everything as accurate as possible. And there's lots of elements to this, one of which is the mount. You need to keep the camera as stable as possible. Before I move on to the rest of the technology, we have got other camera systems. So the ultracams were called nadir cameras. They look vertically down at the Earth, but we also have oblique systems, which is a set of 5 cameras. So you've got one pointing straight down, and then you've got another 4 cameras pointing at 45 degrees. And this gives you more of a view of the faces of buildings. You get more of a picture of the sides of buildings and extract information that way. Then increasingly, we've got hybrid cameras, which are a mixture of sensors. So we use this in our project in the Netherlands, where you've got the 4 oblique cameras, you've got the vertical camera, and you've also got a LiDAR sensor, which is a pulse and return laser sensor, which automatically creates a 3D image of the Earth's surface. And again, one of the trends of technology is to combine different sensors into the same platform. So you're not having to fly something twice if you're requiring a LiDAR survey and an aerial photography survey. So moving on to technology. So as I mentioned, positional accuracy is important. And this is one of the key bits of technology that will enable this to happen. So as I mentioned, we are in an aircraft, which is a highly turbulent environment, and we have got a very sophisticated GPS and navigational system. What we're needing to find out is the position of the aircraft, the camera, at the point of every picture was taken. We're also needing to know the orientation of the aircraft. If you imagine our aircraft is going along and it's still got some rolling and pitching and yawing, it's moving all over the place, even with the mount. So we are needing to record the orientation of the aircraft at the point of capture at every photograph. So we've got 2 bits of kit that enable us to do that. So we've got a GPS system, which is an antenna on the roof of the aircraft, which measures the GPS location. And we've also got what's called an IMU, an inertial measurement unit, which is a series of gyroscopes which keep a record of the roll, pitch and yaw of the aircraft. And if we sync those 2 data sets together, we get a timestamp and we get the orientation. We can get a very accurate measure of the position and the orientation of the aircraft when each photograph was taken, which is really crucial when we are going to be merging them all together. A little bit about aircraft. So we use, there's a variety of aircraft that are used for survey. So typically Cessna turboprops. So we operated a couple like this last year. Aircraft choice is very crucial depending on what type of survey you're going to be doing. So the range is useful. So you want a good long range so you can make the most out of those precious weather windows. And you need to hit a sweet spot with ones that have got a decent range and a decent amount of speed, and also can fly to the height you want it to. So typically, survey aircraft you can get 5 or 6 hours. So it gives you that a decent amount of survey time. And we've also got some aircraft where you have some surveys where you want to fly very low and you have to fly very slowly. And again, you have different aircraft types for that as well, where ones you can go down to about 110 knots, even lower, if you want to fly very high res and low surveys. So again, aircraft choice is crucial depending on what your project outcomes are. So, as I mentioned, the purpose of this talk, we're looking at mass capture of nationwide datasets. So in the UK, our flying season is between March and October. So areas captured on a 3 to 5 year cycle, we're now trending towards and almost hitting a 3-year update cycle. So if you're maintaining a national imagery layer, your targets are determined by the ages of the existing imagery. We also have customer requirements as well. And from that's how we establish our target blocks. So again, 50,000, maybe 80,000 square kilometers of capture a year, depending on what update you're trying to achieve. So critical is flight planning. As I mentioned, it is a very busy airspace, the UK. There are a lot of restricted areas, so we have to be very careful in our planning. We use aeronautical charts, and a lot of conversation was with the air traffic control authorities. So within this controlled airspace, which, for example, much of the southeast over London, there are 4 stacking zones on the corners of the M25 where you probably have been circling in an aircraft waiting to land at Heathrow or Gatwick. These are between 8 and 16,000 feet, which is a huge problem. If you think you're a survey aircraft and you're going to be hanging around in that airspace for 4-5 hours, most civil aircraft and the air traffic controllers are expecting aircraft to take off and go off to France or Spain. But if someone's going to be hanging around for 4 hours, it's the air traffic controller's responsibility to monitor that plane. So if they're at all unsure if the airspace is too busy, they won't let you in. So between 8 and 16,000 feet over London is a huge problem. But if you go back to our 2 camera systems, we had one with a long focal length lens, which enables us to fly at 19,000 feet, which did alleviate that somewhat. Now we need to flight plan. So we've got a survey, we need to cover our area. And we do that with hugely overlapping exposures. We usually fly either east-west or north-south. And this is guided by what air traffic will reasonably accommodate. The software shows the footprint of each frame on the ground, and one of the most crucial things is overlap. So we fly with a very high overlap, 80% forward overlap from frame to frame, and 30% from flight line. And this is crucial for the accuracy of the data and downstream production. So once you've established a flight plan, it will create GPS waypoints, which will trigger the camera when you're in the air. And in all this busy airspace, we need to apply for non-standard flight plans to enter any controlled airspace, which does cover a lot of the UK. So we apply beforehand with our flight plan. This is what we want to fly, which this level, the call signs of the aircraft, all the relevant details. And then you will get a permission to fly for the season. But this might not necessarily get you in on the day. You still need to activate that on the day. So that is one of the impediments. The second impediment to flying, especially in the UK, is the weather. So for survey, we need absolutely clear skies. So probably not like that photograph at the top where you've got little puffs of cloud in the blue sky. You need minimal or no cloud, so no features on the ground should be obscured. And we're also guided by sun angle. So we've got specifications for most projects with a minimum sun angle, which dictates our capture season between March and October. So yeah, the lower the sun, the longer the shadows, and the lower the image quality. So we've got specifications of sun angle as well. So that all guides when and where we can survey. So I've got a little animation to show you, a typical year in the UK. This is 2019, and taken a day at a time through the whole season. As you can see, there are very many days where it's cloudy, especially up in Scotland. So you really need to maximise every opportunity. If you're thinking you've got 80,000 square kilometres to capture, and you're in a really good day, A really good day, you could probably get 1,500 square kilometres of capture, maybe 2,000. So you're looking at needing 40 flying days, or 20 if you've got multiple systems. So you really need to maximise every opportunity. So again, the technology of the large camera systems helps, and also having that experience of working with the weather, knowing where to go and being ready is critical. So data capture, how do we go about it on a typical day? So most of our survey work takes place over the transition zone at flight levels. This is with the airspace designated and controlled by the air traffic authorities, where aircraft is separated into flight levels by hundreds of feet. So the vertical distance between the aircraft and the ground is known. So yeah, typically we'd be up to maximum 19,000 feet with our long lens system. Now the vertical distance to the ground actually does vary due to pressure variations. So if you're in a high pressure day, which is generally you are, you're serving in good weather, good sunny weather, it's high pressure, you're actually at a higher altitude relative to the ground due to that pressure variation. Now the height, the variations of the height to ground is crucial. So the higher you are, you actually get a little bit more overlap, but you get slightly less resolution, which is usually fine, because the critical thing in all of our surveys, you want to maintain that overlap for the accuracy of the data. So again, yes, we perform surveys in high pressure days, so flying higher than the flight level suggest, and this shows you what we're like over the ground, and an illustration of what the overlap looks like. So if you're raising those two aircraft, the actual overlap will slightly increase on the ground, and it also varies with topography as well. So you're going to get a higher overlap over higher ground. So you need to make sure that over the lower ground, your minimum desired overlap is maintained, and that is all done in the flight planning. Data capture. So as I mentioned, the aircraft endurance is about 5 to 6 hours. So assuming skies can remain clear and air traffic keeps us in the airspace, we'll use the full endurance of the aircraft, and we'll return to base and land at the nearest airport to refuel. And when we're trying to maximize our opportunities, the planning of where we're going to go, where we're going to refuel is critical. So at the height of summer, we'd want to try and get multiple missions in a single day, because at the height of summer, you probably have a survey opportunity from 7 a.m. to 7 p.m. So you want to get 2 missions in that time. So as well as a pilot, we'll have a camera operator in the back. So the main role of the camera operator is to operate the imaging sensor equipment, making sure the flight plans are followed, and communicating to pilot. Now the pilot will be communicating with air traffic, and air traffic might well say, well, you've got 20 flight lines, can you please start at number 20 and work north, or sorry, I can only accommodate you on the first 12. So there will be ongoing communication with air traffic via the pilot during the capture day, because we're working in very busy airspaces, and especially over London, you could be kicked out of that airspace at any time. And the other role of the camera operator, again, is to verify the real-time coverage. You can QA the data. You can see and note down if there has been any cloud or any images that might not have come out. So again, you have an in-flight sanity check on the data. So assuming you've had a good flight, you have been let in, you've got all of the data you can, the next stage is processing. So this is going to take the imagery from a load of individual photographs taken of our 3D lumpy surface of the Earth. And the ultimate goal is producing a 2D image that absolutely matches your mapping projection. So in our case, we are creating data that in the UK that matches the Ordnance Survey mapping grid. So we've got 4 main products that come out of the photography. As I mentioned, we've got the the camera has 4 bands, a red, green, blue, and infrared. And our core product is probably our RGB orthorectified photography. So what's orthorectified? Orthorectified is georectified and matching your mapping grid. So rectification is a warping of the imagery from so it fits over a 3D surface onto a 2D mapping projection. Also, we've got we can produce the color infrared, or we can produce our 4-band imagery, red, green, blue, infrared orthophotography. And we also got 2 other key derived data sets. So we can produce a digital surface model, which is a 3D model of the Earth's surface, and also a terrain model as well, which is derived from the DTM, which is actually a surface model with buildings and vegetation removed. So these are our key core products. So it's quite a lengthy process, especially when you're dealing with tens of thousands of square kilometers of imagery. So we've got quite a few processing stages to get from our starting point to our end point. So initially we're doing cloud checking. And then there's a very critical phase, which is the IMU and the GPS processing, which is getting our accurate positional fix and orientational fix of the aircraft. And then there's work on color balancing. And again, aerial triangulation I'll talk you through, which is further accuracy improvements. And then once you've got a really accurate position for each individual photo, they can be mosaiced together and orthorectified, which is the warping into our map projection. And finally, there's some editing, and then we can tile it out. So I'm going to take you briefly through some of those stages. So cloud checking is pretty straightforward. I haven't got a slide on that. And that's typically done by the flight operations team in preparation for their next survey. They mark down what there needs to be flown and then adjust their flight plans and refly it. Now, GPS and IMU processing is one of the most important parts of getting our data accuracy. So I keep saying we're taking a load of individual photographs over a 3D surface. And this slide shows that how important the orientation as well as the position of the aircraft is. So if your aircraft is moving, the orientation and the direction that the camera is facing towards the ground is changing ever so slightly from image to image. And you're going to need to track that absolutely accuracy. So that's where the IMU comes in. And it's got a set of highly accurate gyroscopes which are constantly measuring the roll, pitch, yaw of the aircraft to a high degree of accuracy. And together with that, we've actually got the GPS. So GPS is a GPS antenna on the roof of the aircraft, which gives us our positional fix in X, Y, and Z. And this is then triangulated with both satellites while you're in the sky, and also we post-process it using base stations on the ground, which base stations are maintained by the Ordnance Survey, give us constant stream of highly accurate positional data every second, so we can actually use those to triangulate the airborne GPS and get an even more accurate fix on the GPS at a particular moment in time to the nearest second. So once we merge that with our IMU data, we've got our XYZ and our roll, pitch, yaw, or omega phi kappa orientation of the camera system at the point of capture. Now, this is interesting. So what we need to measure is actually the position of the camera system, but the antenna of the GPS is usually on the roof of the aircraft. So we need to account for the difference between where the antenna is and where the focal point of the camera is. So again, we need to measure those measurements to factor that into our GPS IMU measurements. So all these little things are critical. So when we're working with thousands of images, we need to mosaic and overlap together. The position of them relative to each other needs to be absolutely accurately worked out. So all these little things, it's a bit like an aggregation of small marginal gains help. So our output from the GPS Imu processing is the accurate GPS location of the sensor at the moment of capture of each frame, and those critical roll, pitch, yaw angles of the aircraft at the moment of capture. At the same time, we've got a load of images, and we perform radiometric corrections, which is basically color corrections. So you're capturing over a 3 or 4 hour time period. The lighting conditions may change. The brightness and darkness of the features on the ground may change. Now the technology, there are a lot of really clever algorithms which account for things like the angle of the sun at the point of every capture. So all these little brightness variations can be accounted for, a lot of it by automated algorithms. So this slide kind of shows the before and after. So where you've got brightness variations in every individual image, we do a lot of color processing. So your individual images are very even in color, which when you're going to be mosaicing them all together, you're going to get as even a data set as possible, where you've got all the color information is still visible. You're not losing data in the shadows. You're not got image burnout on the tops of roofs. So again, it's another critical factor in the look of the data. Now, to position and accuracy, the second part of our positional accuracy is aerial triangulation. So again, this is further refining the measurements of the relative position of every individual photograph relative to every other one. So the inputs are our position with the GPS position and the roll, pitch, yaw. And what the software does, it puts all those images together in your flight, several thousand. Then it finds tie points, so common points of the same pixel brightness value. And it uses those to make micro adjustments to the position of every image relative to every other image. If you think back to our high overlap, there are going to be hundreds of thousands of tie points. And then on top of that, we introduce ground control points, which are the green triangles in this highly complex diagram. Now, control points are known points on the ground. So we take GPS survey equipment and we survey features that you can see in the photography, typically things like road markings, manhole covers, and we can measure those to a 1 to 2 centimeter accuracy. And then we plug that into the software, and you can say, well, this point has got a 1 to 2 centimeter accuracy. And what it does, it tells the software that every single image that road marking falls on, and there might be 10, 20, 30 with our high overlap, it tells them the absolute 1 to 2 centimeter accuracy coordinates of that pixel. And it just helps nail down the accuracy of the whole block. So a block of data is every measurements of every image relative to the other image, and it does all these micro calculations to relatively adjust the position of one to every other image in the data set. So it's huge computer number crunching to get the position of every image as accurate as you possibly can. So the upshot of this is, we've got a highly accurate data set. And also another spin-off is that we've got this massively high overlap. We've got all these common pixels, and all of these common pixels will have values. It can calculate the value of X, Y, and Z for every pixel in the data set. So when it's got this amount of information, it can do a massive amount of number crunching and produce a 3D surface model. So with the positional information of every pixel, it will produce what's called a digital surface model, which is a 3D model. This is directly derived from photography. So this again is another product you can spin off straight from your photography, and it's a hugely useful data set for things like measuring building heights, tree heights, line of sight, position of mobile phone mark. All these sort of applications are used in junction with the color information for the photography. It's now got 3D positional information highly accurate, so we can output this at the resolution of photography. So we can do a point every 12.5 centimeters all over your data set, which might be 2,000 square kilometers. So it's a highly accurate data set. And then the last part is the author rectification. So what we're doing is we're taking our series of photographs and we're warping them and projecting them onto a 3D mapping surface. And there's a couple of ways you can do this. You can use the DSM, which is a surface model, and it takes all of that 3D information. So every pixel, it knows its 3D position. And if it's got that information, it can choose where to project it into 2D. The traditional method was actually to use a DTM, which is a surface model, where you've got the buildings and trees removed to do the same thing, and it warps the data. But if you're using a surface model, you've got all this extra information in 3D of every building and every tree, and it gives you a massive amount of information to be able to flatten that image accurately into a 2D mapping projection. So the next slide will show the difference. So if on the right we're using a DSM, and because you've got all that 3D information, what it will do is choose the most vertical photograph for that individual pixel, and therefore you get a very vertical image of the Earth. Whereas if you're using the DTM, you haven't got quite as much information, and for tall buildings you might get a bit of building lean, and that is critical if you're wanting to derive data on the ground from the photography. You don't want to be losing information under that building. So a technological advance is the ability to create a true ortho using the surface model with all that 3D information when you're ortho rectifying and projecting it onto your 2D mapping plane. The final part of the jigsaws, once we've ortho rectified and flattened our mosaic of photographs into 2D, then we do have to tidy up any seam lines and join lines between the individual photographs, and this is where the evenness of color helps. So we mosaic it all together, and then we typically split it up, we chop it up, tile it up into 1 by 1K tiles in the UK on the OS grid. But from this point you can reproject it whichever way you choose, and chop it out and tile it out in whichever way you choose. And then from there we deliver it in whichever imagery format the customer required, typically TIFF, and then we've got compressed data sets like JPEG or ECW. So this is the data we deliver out to customers. So again, going back, we've got our core products. So we've got the ortho photography. And again, because we're capturing our 4 color bands, red, green, blue, and infrared, the infrared is absolutely synchronous to the red, green, and blue, which is really useful for vegetation analysis, growth analysis. So that's the ortho photography. And we can produce 4 bands as well, because we capture everything and produce everything in 4 bands. And again, another illustration of standard ortho versus our true ortho using the DSM, and again showing how much more detail. And again, the surface model, we have that as a product. We generally edit out if there's any noise and spikes, typically over water areas. We edit it out. That's a highly useful product. It's got loads of applications. So we remove spikes and artifacts, and then we can go one step further and produce a DTM. And again, a highly useful data set, a digital terrain model called a bare earth model. So the buildings and vegetation are removed. This is a semi-automated editing process, and again, using quite a lot of computing power, a bit of manual interpolation. And the applications of removing our buildings and vegetation most primarily are flood modeling. So it's a hugely useful data set for flood modeling, environmental impact, development planning. And 3D visualization. There's all sorts of applications for the height products. And again, once you've got a DTM, you can automatically derive contours as well for mapping. So it's, again, all of this is directly derived from the photography and part of our standard production process. Just to wrap up, I've got a few slides on the uses of aerial photography. So probably the most obvious one and the biggest driver for a lot of the update programs is topographical map making. So from our historical slides way back, when it started to be done commercially, it was used for the update of topographical mapping. So any change detection is hugely valuable. And again, infrastructure planning again is a huge amount of change. It's all about the mapping of change. We live in a very complex environment. There's always changing, so there is a demand for the mapping of that change, whether it's buildings, roads, land use. And again, things like event planning as well, logistics planning, and land management. So there's all sorts of applications. And we also sell for archaeological purposes as well. We sell to the likes of the British Geological Survey. And again, things that you might not see in the ground can be revealed from the air. I think in 2018, there's a lot of news articles about aerial photography revealing the traces of old settlements and field patterns when it was an exceptionally dry summer and all the fields had dried out, and you could see these features from the air where you hadn't previously been able to see them in fields. And again, change detection. There's a nice image of the change of the London Olympic Stadium. And again, we haven't done this, but there is a lot of call for response media as well. Flights responding to media events, floods, earthquakes, and things like that. So again, it's got a lot of uses over a wide variety of disciplines. So Getmapping, we sell to a variety of customers, principally central government and local government, but it's quite a wide consumer and customer base. So that pretty much is a whistle-stop tour in 45 minutes of how we capture and process aerial photography on a mass national scale. So happy to take any questions.